Okay, so this is the ChemCompute website, and this semester we'll probably use this for our final lab of this semester. I'm still working out the details of that, but this seems like a good approach for us to use. And we're going to be using the GAMES computational chemistry package. And you can see up here at the top, ChemCompute has access to a bunch of other ones. Sci4, for example, is a different one. Jupyter is a Python programming language notebook that you can use. We have Tinker, NAMD, right? There are lots of different ones. But we're going to go ahead and use GAMES. And GAMES lets us do ab initio computational chemistry calculations. So the first thing you need for any computational chemistry calculation is the program needs to know what your molecule is, and what shape it takes. And so generally you have some way of specifying the geometry. It's usually a text file, but there are nice front ends to be able to actually draw your molecules. For example, we're going to go ahead and do a calculation for ammonia, Nh3. And this web interface gives you a nice way you can just search for a molecule and it'll build it for you if it already knows. You can build it from scratch as well, right? We could just put in a nitrogen and attach 3 hydrogens to it, but we can also just search for the molecule. And if you've done something from a previous job, you can load something from that previous job. That's a very common thing that's done in computational chemistry. Okay, so we make the Nh3. Well, I'll go ahead and search and add it again so you can see the next part. And so then down here, what it does is it symmetrizes the molecule. So it finds, it has an axis of symmetry and gets it roughly the right shape. So this is just to get it, if you drew it kind of crooked, then it'll get things sort of, reasonable bond angles. I'll go ahead and hit next. And this is where we set our parameters for our calculation. So quantum mechanical calculation. We can name our input file whatever we want. We specify the charge and multiplicity. So this has to do with, do we have multiplicity is do we have unpaired electrons? And charge is this an ion? And then the type of calculation we do there are different ways of doing this. A single point energy calculation leaves the geometry fixed and just finds what's the lowest energy for that particular geometry. The more common thing that's done is what's known as a geometry optimization. And this is where the molecule, the program automatically adjusts the bond lengths and angles of the molecule and finds where the lowest energy point is. And that's going to be the geometry of the molecule that it'll adopt. Molecules tend to go towards the lowest energy. And we can calculate other things. So we can do infrared, find the vibrational frequencies, find some thermodynamic properties. And like I said, you can calculate NMR. So we'll go ahead and do the IR and see where the vibrational frequencies of this molecule are. And then here's our basis set. So we have some of these ones that I've mentioned, right? So our most basic one, STO3G. We have these Popel type basis sets. So 6-311 G star star. We have plus over here. And there's this correlation consistent basis set that I mentioned, OG, CCP, VDZ. And then some other ones over here with, I don't even know what these ones are called. So we're going to go ahead and use this split valence, triple zeta, polarization, and diffuse functions basis set. It doesn't particularly matter. And then we have to pick our method. And so this automatically uses a type of method called density functional theory. We haven't talked about that at all, and I don't feel qualified to talk about it honestly. But this is something that's a little bit different from either variational theory or perturbation theory, but allows us to find, the quantum mechanical properties of the molecule. Okay, and so then we can put this inside of a solvent. We just want this on its own. And then this is where there are different, these are the names of the different, basically supercomputers or computer clusters that we can use to do these calculations. Okay, so once we're ready to go, we only get to use one processor core because this is just a free service that's being offered by a research group. We submit our job. And so this is the actual file that gets sent to the program. So you can see it's a bunch of text, but the program knows how to interpret that. All right, and then we can actually watch our computation go as it's going, right? And so it's going through and calculating different properties and minimizing the energy according to variational theory. And so we wait. And so we see how long, this one shouldn't take too long. Ammonia is not that big of a molecule. So I should have tested this before I started this video, but I didn't. So we might be sitting here for a little bit. Let's see if I can fill the time. Once this is done, we'll be able to see the wave functions, see what the energy is, see the different orbitals, and also get the vibrations of the molecule as well. So I think it might be the vibrations that are making this take a little bit of time. All right, so I'm going to go ahead and pause, stop the video here, and we'll look at the calculation once it's complete.